Welcome back. In this video, we'll continue Chapter 7 in our coverage of thermodynamics. And now we're going to focus on the second law of thermodynamics. Now, the first law we understood from the conservation of energy theorem applied to thermodynamics was just simply an accounting of the energy flow in and out of a system through either heat or thermodynamic work. But even with that understanding of the first law, it was clear that there were certain processes that were perfectly fine with the first law, accounting of the energy, but were well understood to be absolutely impossible processes. So for example, if you take a system where we've put a diathermal boundary between the left and right side, and on the left and right side we have the same substance, 1 liter, 1 mole, and they're both at 300 Kelvin, we know that with the first law that there's nothing violating the first law that says that the temperature of the left side can get warmer while the temperature of the right side gets colder in a process where you eventually end up to a state where the left side is at 400 Kelvin and the right side is at 200 Kelvin. That's actually perfectly valid. Now, of course, I could have created that situation by taking this system over here and splitting it up into 2 parts and putting one on a hot plate and putting one on a cold plate and then putting back together to get this system. But what I'm saying is that this is done without any interaction with an external system. It just spontaneously, all by itself, went from 300 to the left side being 400 and the right side being 200. And that's perfectly fine from the first law point of view, but we know that that's an impossible process. In fact, the spontaneous process, the process that we know that would happen naturally, would be that if we had 400 Kelvin over here and 200 Kelvin here and a diathermal boundary, that this system would actually have heat transfer from the hot side to the cold side until it reached this state over here. So there are many ways of stating the second law. One way, simple way, was done by Clausius in 1854. He said, "No process is possible whose sole result is the transfer of heat from a cold body to a hotter body," which is what I'm trying to explain here. But it wasn't until 1865 that Clausius actually discovered a thermodynamic quantity, which he later named entropy, which actually explains why this direction here is the spontaneous direction and this direction is the impossible direction. So that supplements the first law. This new concept of entropy allowed us to determine which processes were allowed and which ones were impossible. And Clausius came to this understanding by reading a book by Sadi Carnot, which was written earlier in 1824, on the reflections on the motive power of fire. And what Sadi Carnot was trying to do was understand how we could determine the efficiencies and the best efficiency of heat engines. Remember, this was 1824, so this was the beginning of the industrial age, and coal was being used to create engines that were used to do all kinds of, create products and do all kinds of services. And it was a tremendous time where a lot of the economy was changing with these heat engines, and people wanted to understand how to make better heat engines and what were the limits of these heat engines. And so Sadi Carnot took on the task of trying to theoretically study a heat engine. Now, at the time that Carnot was doing this, people thought that heat was a fluid that flowed like water flows from some high altitude to a lower altitude. So in their minds, heat was a fluid that flowed from a hot body to a colder body. Now we know that that's not correct. We spent the last few lectures trying to make clear what heat actually was. But at the time, this was their picture, that this was what was in Sadi Carnot's mind. So that heat was flowing, and he thought, if we think about a heat engine as kind of a device that was put inside this flow, it could capture some of that flow and in the process extract work out of that flow. So the picture that Sadi Carnot had was that there was a hot reservoir and a cold reservoir, and in that flow from the hot to the cold, we could put an engine, a heat engine, and that would extract out some fraction of the work. And what was the efficiency of this engine? And that's what he was working on, all right? Now, it turns out that that even though the idea that heat is a fluid is not correct, the conclusions that Sadi Carnot came up with were all actually perfectly fine, and they still applied. So let's take a look at what he did. So the way his heat engine worked was it was a cycle where you started in some state and you went through some cycle and you came back to the same thermodynamic state, and in that process you extracted out some net amount of work in that cycle. And it's a pretty simple design. You have a hot reservoir and a cold reservoir, and we know heat will flow between them, and that flow is going to be mediated by our heat engine. Here we're going to show that heat engine is just simply a piston cylinder apparatus with a gas in it. So we've learned now that if we take a piston cylinder and we let the gas expand, then the system is going to do work on the surroundings, and that's work that we can use. So in this first step, what Sadi Carnot imagined was that the first step would be a reversible isothermal expansion where the system is in contact with the hot reservoir. So it's now an isothermal process because it's touching this hot reservoir, and then we let it expand. As it expands, heat will flow from the hot reservoir into the gas as we extract work out of it. The next step will be to disconnect our heat engine from the hot reservoir. So now it's separated. It has adiabatic walls in a sense now, so there's no heat that can flow, and we allow it to continue to expand. But since it's no longer in contact with the heat reservoir with a thermal bath, as it expands, then the temperature will drop, and we'll let it continue to expand until the temperature reaches the temperature of the cold reservoir. Once it reaches the temperature of the cold reservoir, we'll put it in thermal contact with the cold reservoir, and then we will start compressing it. So now we're going to put work into the system, but we're going to do this isothermally. So as we put work into the system, it's going to remain at a constant temperature, and it's going to push heat into the cold reservoir. We'll do that for a while, and then we'll disconnect it, and now we will have it separated. Again, we'll have another adiabatic process where we will now continue to compress it. Since there's no heat that can flow in and out of the system, as we compress it, we're putting energy in. The temperature is going to rise from the cold reservoir temperature where it was initially, and when we reach the hot reservoir, then we come back to where we were originally, and we can restart the cycle again. And in this process, we will have work that comes out during step A, work that comes out during step B, work that goes in during this process step 3, C, and then work that goes in during the process D. And the result of this is that we'll have a net positive work that comes out, or that we will be able to extract out of this system. So if I made a plot of the pressure versus volume for those steps, so here's our initial state, state 1, and we do first an isothermal expansion, and then we'll do our adiabatic expansion to state 3, and then we will do a isothermal compression to state 4, and then an adiabatic compression back to state 1, and the area inside this is going to be the net work that we get. So remember, when we do the expansion steps, it's the area under the curve, and then the compression steps, the net work will be the area under that curve, and so the difference of those two areas is the areas inside, and that's the net work that we get out of our engine. All right. So when we look at Sadi Carnot's treatment of this, then the way he looked at it was, okay, we have heat and work. So we have the heat that comes into the system from the hot reservoir. There's the heat that's exiting the system into the cold reservoir, and then there's the work that's exiting the system. So when you write down that in one cycle, all of this should add up to 0 from the basis of the first law. So Carnot defines a heat efficiency as the work extracted out of this engine divided by the heat that flowed into it from the hot reservoir. And there's a negative sign here to make that a positive quantity. All right. So we will rearrange that expression here, and we'll substitute here back into here, and we will get this expression, which we can then substitute together to make this, and then rearrange this, and we finally end up with this simple expression here, which tells us that the efficiency is equal to 1 plus the heat that flows into the cold reservoir divided by the heat that flows from the hot reservoir. Now remember the signs here, so the heat that flows into the system from the hot reservoir is going to be a positive quantity. The heat that flows out of the system into the cold reservoir is a negative quantity, so this ratio is always a negative number, and also the magnitude of the heat flowing out of the hot reservoir is going to be greater than the magnitude of the heat flowing into the cold reservoir because we've extracted some work out of it, so it's going to be less that amount of work, and so this will always be a negative number and a fraction that's less than 1, so this efficiency can never be greater than 1. It's always between 0 and some value slightly less than 1. Okay, so that's our efficiency from Carnot's simple treatment right here. But what you realize from this, and what was realized by many, is that reversible heat engines that operate between the same two temperatures, between the same two temperature reservoirs, have to have the same efficiency regardless of what substance that was inside them. Okay, well, why would you think that was true? Well, it turns out that if you think carefully about this and think, if I can find two different substances which had different efficiencies and use them between the same hot and cold reservoir, I can create a system that violates the second law statement, as Klaus said at the beginning of this video. So in other words, we take a heat engine, which now I'm just going to sort of condense down into this picture where I have QH coming in from the hot reservoir, W coming out was the work, and then QC going down. Then we could run that heat engine backwards. So in other words, if you go back to our cycle here, instead of running it A to B to C to D, we're going to run it from D to C to B to A and backwards. So we're going to reverse the cycle of the engine. And if we do the reverse cycle, what we do is we create something called a heat pump or a refrigerator. So what happens is that the heat that flows, the work that goes into this heat pump will actually take heat from a cold reservoir and push it into a hot reservoir. Now that's, again, a process that would not occur spontaneously, but we're putting work into it, and so that's allowing us to move the heat from the cold into the hot reservoir, right? Now, if I had two cycles, one heat engine running with one substance, another heat pump running with a different substance, and they had different efficiencies, I could couple them together between the same hot and cold reservoir, and I could create a device that would violate the second law. And so you can see that with this efficiency of 1/4 here and efficiency of 1/5 here, I would create a system where this system would take 4 joules from the hot reservoir into the engine, would produce 1 joule of work, and then dump 3 joules into the cold reservoir. And that 1 joule of work would be fed into a heat pump with an efficiency of 1/5, which would take 4 joules of heat out of the cold reservoir and push 5 joules of heat into the cold reservoir. And if you take the net of all of that, then we have no work going into this whole device. So it's summarized here. We have effectively just 1 joule of heat coming out of the cold reservoir and 1 joule of heat going into the hot reservoir with no work involved, by coupling these two systems with different efficiencies. So clearly that's a violation of the second law. We can't have heat just spontaneously flowing from cold into hot. The solution to this is to say that no two heat engines or heat pumps operating between the same two reservoirs can have different efficiencies. Okay, so it must be true then that for reversible heat engines and pumps, they have to have equal efficiencies when operating between the same two reservoirs. So if that's true, then it's independent of the substance that's inside. So let's use the ideal gas as our substance, where we can actually calculate what those adiabatic and reversible adiabatic and isothermal expansions were, to see what our efficiency was and how it would actually depend upon the temperatures of the reservoirs. So for the adiabatic step, we did this in the earlier lecture, where we worked out how the energy flow in the work that was done in an adiabatic step, we found these integrals here we could evaluate for the adiabatic step. So we're going from a hot temperature to the cold temperature, which is from V2 to V3, and then for the other adiabatic step, we're going from the cold to the hot, which is from V4 to V1. We take these two adiabatic processes and we add them together, and we get this expression, because you can see everything factors out here, and then we get this expression, which finally simplifies to this. Okay, so we'll put that one on the back burner for the moment, and now let's consider the isothermal steps. And if you remember, for the isothermal steps, that we had the heat that was just simply the temperature at which the isothermal step occurs. So for the hot reservoir, QH, we have a TH here, and then we have V2 over V1 in this expression. And for the heat flow into the cold reservoir, now this is occurring at TC, so now we have V4 over V3 in this expression here. So if I now take the ratio of those two, which is what we need here for this calculation, then I can plug those together and I get this expression here, taking this over this. And now you see that this term here, which was -1, gives us this relationship here. So finally we find that the Carnot engine efficiency is going to be independent of the substance that's in it. It's just going to depend on the temperature of the cold reservoir and the hot reservoir according to this expression here. So you see right away that we can't get an efficiency of 1 or higher, because you can see that since the coldest you can get would be 0 Kelvin, and that's unattainable because of the third law, which we'll learn about at the end of this chapter. And of course, the highest temperature you can get is not going to be infinity, because the speed of light sets an upper limit on that temperature, because of the molecules can't go any faster than the speed of light. So you can see that it's impossible for you ever to get an efficiency that's equal to 1. The best you're going to do is going to be something less than 1. Okay, so that's it for our treatment of the Carnot engine. Next, we'll look at how Clausius looked at his treatment and found this new state function, entropy.